to search for this very rare type of interaction, job number one is to first get rid of all of the ordinary sources of radiation, which would overwhelm the experiment. This is the Lux experiment, and it's been, there's this now cutaway here so we can see inside. We're looking for exotic particles coming from outer space, passing through the Earth. We're building an instrument that we believe will be sensitive to see those particles, and if we see them, it's going to revolutionize what we know about where the universe came from, why it looks the way it does, and what makes up the universe at the very smallest scale, even inside even scale smaller than atoms. If I make a liter of space, the WIMP hypothesis is that there's a few of these dark matter particles passing through at any given moment. And so in our experiment, what we're trying to do is test that hypothesis by building a instrument which would be capable of seeing those particles, those WIMP particles, as they pass through the experiment, if they were to bounce off of the target material that we have inside the experiment. What we're doing in our experiment is we are basically taking a whole bunch of liquid xenon and we're instrumenting it so that we can see if anything bounces off of it. And so that the key feature of the experiment is that the target material is instrumented in a very sensitive way so that we can find evidence that these particles are bouncing off of the liquid xenon. Knowing what the dark matter is going to tell us about how the universe formed in the early days, why it evolved the way it did, and why it looks the way it does today. When we look up in the sky today, we see these vast galaxy clusters, for example, and then we see these vast voids that are free of any galaxies. There's no galaxies at all. Knowing what the dark matter is would provide an explanation for why the universe has that kind of bubble-like structure that we see today.
That actually, has a little bit of mass.
The original. Wait. Oh, so wait, isn't it? It wouldn't be the massive part. No. What you're looking for is right. A neutrino.
So this is the inner cryostat. A cryostat is like a thermos. So xenon is very cold, and we need to keep it cold. So we need a big metal container that we can put 10 tons of liquid xenon in.
So there will be about 300 tons of ultra-pure water filling this room. As we start to study the evolution of the formation of structure in the universe, we see that normal matter is not enough to form the structures that we see, galaxy clusters, superclusters, and whatnot. We need extra matter there to act as the seeds by which other matter can collapse onto it. So there's an intrinsic value in understanding the universe better than we currently do. And knowing that there's dark matter out there, but we can't explain it, this is a very fundamental problem. It is a very fundamental open question, exposes a big lack of understanding that we have about the cosmos. Not till Thursday. The scientific impact of a discovery of dark matter will certainly be very much up there with the discovery of the Higgs and gravitational waves, even more so because we sort of knew most of what we needed to know about the Higgs before it was discovered. Gravitational waves, we sort of knew how they were going to interact. We have no idea what dark matter is. It represents a fundamentally unknown component of our understanding of the universe.
That'd be great. I mean, I got you, but that's totally fine.
Yeah, it's not the same thing as finding a new particle, but it's helping us understand the universe we're living in. And that's, for me, that's the motivation. What is this great place I live? And right now, 95% of it is a mystery. You know, isn't it great to be able to say, I'm helping to understand what that mystery is or isn't at this point?
Which direction?